Great, thanks. So thanks everybody for inviting me. I'm glad we're able to make it work on short notice. It's a pleasure to at least be at Northeastern virtually. So today I'm going to be telling you about general covariance with stacks. I think the title is nice and vague, but don't worry, things will get particular very quickly. So the usual structure, I'll get some motivation out of the way, and then I'll give the big picture about general covariance using more like stacky language, which I'll try to make as concrete as possible. And then we're going to go over some results in deformation theory that sort of recover classical results in physics in terms of stuff like Noether's theorem, but also enhance them along the way in a pleasant way, at least I found. So there's a few caveats that I have to state here. General covariance has quite a long history. So the basic idea is that we'd like to understand when the Diphyomorphism group of some underlying manifold or spacetime is a symmetry of physical data associated to that field theory, right? So if you have like a field theory that's coupled to a gravitational background, then we'd say, okay, we have some physical field like a fermion or a boson, but its trajectory, right, its dynamics are influenced by the presence of a gravitational field, and that presence computationally just means there's a metric that's involved in the computation. And so that's going to be our focus. That's the path laid out in the early 20th century with the advent of general relativity. It's saying, okay, we're looking at field theories coupled to Riemannian or Lorentzian metrics, although we'll be sticking with the Riemannian case here, sort of without loss of generality. But it's also, I suppose, important to note that in the work of Costello and Gwilliam, which I primarily follow, they stick to the Riemannian case because that's how they end up performing quantization. So the goal here is to describe general covariance for these curved spacetimes, is how I suppose they'd say it in the physics lingo, using the BV formalism. The Batalin-Vilkovisky formalism is sort of like a derived geometric enhancement of the usual way that people might view field theory. And the eventual aim is seeing how we might recover equivariant observables. Again, sort of a la Costello and Gwilliam. One vague comment that I would like to make is that I get the impression, or I've gotten the impression over time, that looking or considering the BV formalism to do something like, you know, a boson in a gravitational background or a fermion in a one-form background, or, you know, space of connections, is that the BV formalism really does this nicely because it packages a lot of data in a clever way. And so hopefully, although I know that what I've just said is rather vague, this will become clear during the course of the talk. And in our case, even though I did mention connections, or in particular connections modulo gauge, I'm going to be focused on the quotient space, or in particular the quotient stack of metrics up to diffeomorphism. Okay, so I'd like to make one more quick comment. If I'm going too fast, please interrupt me and tell me to slow down. And I suppose in particular, if you have questions, please stop me to ask them. My preferred form of giving a seminar talk is if it's a little bit interactive, as opposed to just free, I suppose. Okay, so speaking of free and interacting, let's just consider a massless free scalar field here, a free field theory. So the physical fields here, I would say, are just the fields are smooth functions on a manifold X. And there's a piece of background data, a fixed piece of background data, a Riemannian metric G. And the action functional that sort of defines the dynamics of the fields is exactly this. This is a function which takes, or a functional rather, I would prefer to say, that takes the function phi, a scalar field, and spits out a number, and the number is exactly this. It's the integral of phi Laplace phi against the Riemannian volume form. And if you perform functional differentiation, you'll find that the Euler-Lagrange equations are exactly whenever the Laplacian of some function is 0. And so this particular phi would be living inside the critical locus of the action functional S sub G. So there's a particularly nice property that these fields have, or rather that this equation has. And that's if you have a diffeomorphism F of the manifold X, then we have this sort of equivariance property that the pullback of the Laplacian of phi is exactly the Laplacian of the pullback of phi, where the Laplacian is now defined with respect to the pulled back metric. So in the literature, you'll often see this called the commutativity of diffeomorphisms with whatever differential operator you have, in this case, the Laplacian. Although often, I mean, the word equivariance is used, which I would say is certainly more rigorous. And so there's a key maneuver that we want to make here. We replace the original fields, the original smooth functions, with a differential graded space of fields, right? So this is like a homological enhancement of the original thing. The idea is that we put the original fields, in this case, it's scalar field in degree 0, and in degree 1, we put like a linear dual to the smooth functions. And there are some functional analytic choices that end up getting made there. In this case, we make the choice that we want to look at densities. Densities on X. And what happens is the differential exactly encodes the dynamical data of the Euler-Lagrange equations, right? So in this case, the differential Q sub G is essentially just the Laplacian, except it's slightly modified to land in densities as opposed to smooth functions. So this is really nice, because in the original fields, and if we were just considering smooth functions, there was no reference to the metric, right? Even though the metric is a very significant piece of data in the field theory. So what we're doing here is we're saying, okay, let's consider this new differential graded space of fields, and we're going to make the metric, give it an explicit dependence on the metric. And the collection of all such f sub g defines a DG vector bundle, where the fiber is this particular theory. So I would say that this DG vector bundle here parameterizes the family of free massless scalar fields over the space of metrics. And there's a key quality here. This equation in the middle, sorry, I feel like I stuffed a lot into this slide. But this equation here in the middle, this equivariance property of the Laplacian with respect to diffeomorphisms, tells us a little bit more about this DG vector bundle. So note that this equation works also for QG. They're totally equivalent because the volume form, or the Riemannian volume form, is, as one might say, manifestly covariant. So it also commutes the diffeomorphisms, and this equality here means exactly that given a diffeomorphism, we get an isomorphism of field theories, right? So the idea here is we have this DG vector bundle F over M, and if you have two fibers of this vector bundle that are related by an isomorphism, or sorry, related by a diffeomorphism, they're isomorphic to each other. So even though the dynamics might ostensibly look different, they're really equivalent, and the diffeomorphism provides this equivalence. This is sometimes called diffeomorphism invariance in physics literature. That's like slightly abusive language, I would say. It's more like diffeomorphism equivariance. And in fact, there are physicists, for example, Robert Wald, who are very careful, and I would say more respectful of the mathematical terminology, but this is totally fine. I think using the word invariance is, of course, excused to some degree, because there really is this explicit isomorphism. And this is really much of the content of general covariance classically. And we're giving it, I would say, like a clear manifestation using this differential graded language. Just a quick remark, but first I need to have some water. Oh, I suppose I've actually already said that. So, well, the kernel of the Laplacian is the same as the kernel, of course, of the Laplacian with that volume form attached. And so the point is, right, even though these might be different, they're actually isomorphic. This is the actual quick remark I'd like to make. Is that we have an interesting thing going on here. So if you fix a metric G, there's a pretty good shot, honestly, that it's going to have some isometry group, right? In other words, a subgroup of the diffeomorphism group that fixes it. Right, so the diffeomorphism acts, the diffeomorphism group acts on the metrics, and we might have some stabilizer of that group action. There are manifolds out there that have metrics that have no isometries, but certainly in a lot of instances, if we're looking at Rn or Minkowski spacetime, or de Sitter or anti-de Sitter spacetime, or Schwarzschild-like spacetime. Really, the majority that get considered in theoretical physics, or certainly like classical, I would say theoretical physics, they have isometries. And so we'd like to know how to deal with that situation. By the above computations, the isometry group acts on the critical locus of the Laplacian. And indeed, it acts on the fiber above the fixed metric G. So if G is a fixed metric and F sub G is the fiber, then we have an action of the isometry group. And so just as an example, just to make things a little bit more concrete, we know that the isometry group of the manifold Rn with the flat metric, which I'm calling eta here, that isometry group is just On, semi-direct product with Rn being the group of translations. And so if we have an element alpha in that isometry group, then if the Laplacian of phi is 0, then the Laplacian of alpha pullback phi is also 0, where in that case it's just precomposition. So we have two distinct things going on here. We're saying, okay, you have an isomorphism at the top of the slide where we have two separate fibers, right? So when one fiber gets dragged to another fiber, there might be an action of the diffeomorphism group on the fiber as it's sliding along. But on the other hand, on the bottom of the slide here, we have also that certain subgroups stabilize the point G, and therefore they act on the fixed fiber. So the preceding computation in the last slide is telling us that F over M is a D equivariant DG vector bundle, D here being the diffeomorphism group.
Sorry to interrupt. What's the grading here?
The grading, well, in the case here, we just have smooth functions in degree 0 and densities in degree 1. And this is what we're doing the whole time. I'm going to be constantly referring back to this example. Some of the results that I state later on, and even the definition of general covariance that I'll posit momentarily, work for free theories that have different field content, but by and large, they're concentrated in degree 0 and 1. Although, well, anyway, I don't want to make any additional comments here because I would take us too far afield, but is that satisfying?
Yeah, thanks so much.
That's very cool. Yeah. All right, so yeah, so this computation here at the top of this slide says, okay, F with this differential Q that also depends on the metric is a diffeomorphism equivariant DG vector bundle. I've always been, a fan of slapping as many adjectives as possible onto the word bundle, so this really works nicely for me. And I'd like to note, and this is I would say key at this point, is that because the differential operator we've been considering so far, the Laplacian, is linear, this is a free theory. If we had an interacting field theory, then our differential operator would be non-linear, and I'll make a comment about that in a moment. But just to get a definition thrown up for us, I'm going to state here that if we have a DG vector bundle that sort of defines this family of free field theories on X, then if it's diffeomorphism equivariant as well, then we say that the theory is generally covariant. So we're packaging this equivariance property with this language. I'd like to state, I would say this is probably like more of a cultural remark, that this is a broader definition than usual for a lot of physicists that I've interacted with, at least here at UMass. They really only want to consider diffeomorphisms that are inside the connected component of the identity, which is totally legit. There's a reason why that happens, and we'll see why that's significant later. But I thought I should mention the caveat that here I'm not restricting to just the connected component of the identity of the diffeomorphism group. Yeah, okay. Any questions so far? I feel like I might be moving a little fast, but maybe that's just because it's been a long day. Okay, well, if no one has questions, I'll move on, but please, anytime you have a question, please interrupt. Noah's question is very good. Okay, so you might be thinking to yourself, well, what about Battelle and Vilkovisky formalism? I gave that compound Russian name earlier. Why haven't I brought it up yet? I have actually brought it up implicitly, as some of you probably already know. So the central step of the BV formalism is to replace the usual fields, which earlier were just smooth functions on the manifold X, with the DG space of fields, where the D in the DG is exactly capturing the dynamical data of the field theory. And there are a lot of things go into defining a BV field theory. For example, you need a -1 shifted symplectic pairing. And in our case, this is pretty easy to define. So if you have something in degree 0, you have a phi, and then you have a density mu in degree 1, then the -1 shifted symplectic pairing is just you integrate their product. All right, nice and simple. And by and large, this is what that -1 shifted symplectic pairing looks like. Another advantage of this is that you can write the action functional as the pairing evaluated on phi and the differential of phi. So just to summarize, really, the point here is that we say a family of free BV theories is generally covariant. It is such as a DG vector bundle in the sense that I stated on the preceding slide. So really, we've been doing BV field theory the whole time. And then the differential graded space of fields is meant to define sort of the derived critical locus of the action functional S. If people are interested in that, we could talk about it afterwards. I don't want to load too much stuff on you. But whenever you go and read a paper and you see someone says, all right, we're looking at the derived critical locus, that means they're just looking at this DG space of fields, where the differential is exactly the differential operator in question. Okay, and then what about interacting fields? So far, we've only been doing free theories, right? So an action functional for such an interacting theory might look like this. So this action functional looks a lot like the free scalar field, except we have this quartic term, this phi to the fourth, that makes things a little different, obviously, right? And indeed, if you compute the equations of motion, the Euler-Lagrange equations, you get Laplace phi plus phi cubed is 0, which is very much nonlinear. And so, yeah, some problems arise. I mean, the first one is that finding harmonic functions, in other words, functions that satisfy Laplace of whatever is 0, is, well, it's kind of easy, or I would say relatively easy compared to finding solutions to this differential equation. For this differential equation, by and large, it can get very complicated very fast. And so usually we deal with the interacting case only perturbatively. In other words, to encode some non-linearity, each fiber, instead of just being a DG vector space, has to be an L-infinity algebra. For those of you that don't know what an L-infinity algebra is, it's fine. I know it's scary. It's a scary lexical maneuver, but all it really means is that on top of being a differential graded vector space, which might have a low bracket of a differential, it has some higher bracket that encodes the nonlinearity. So in this case, we have some map L3 that takes three copies of the scalar field and gives us a density in the way one might expect given the equations of motion, right? So in this case, the equations of motion would read, L1 phi plus 1/3 factorial L3 phi is equal to 0, where L1 is sort of the lowest bracket, and it's just the differential. Oh, oops. All right. So it's not hard to show that this particular example is generally covariant as a family of interacting BV theories, because diffeomorphisms behave really well with respect to just taking powers, which is what we're doing. That makes this equation nonlinear. And generally speaking, it's really adaptable, I would say, and I work it out in my dissertation. But for the purpose of this talk, we'll just stick with the free case. I just thought I should say that it's not so bad. And so just a quick summary so far. So just from like a broad perspective, I would say the traditional way that people thought about solutions to some differential equation corresponding to one another was under equivalence, under an equivalence that looked like the isometry group, right? Like remember, we had the Laplacian on Rn, and we had phi, and if you had some element of On or On in a translation, and you hit phi with that, it was still still a solution of Laplace's equation. Now, in this way that we've packaged general covariance, we're saying that there's actually an expanded notion of equivalence, where you can change the underlying data, like the metric G, as well as changing the data on the fibers, but we still have equivalences. This is pretty cool. So the hope then is to consider the moduli space of metrics modulo diffeomorphism in a manner which remembers the equivalences under the isometry group, right? We don't want to just mod out metrics mod diffeomorphism and sort of like lose all the data of the fact that there are isometry groups. In stacky language, you know, like an automorphism group of a fixed point in the stack. So we need stacks. And so that's what we'll be talking about next. Are there any questions so far before I move on? I'm getting even more excited now because I think stacks are like the bee's knees. So really, please do slow me down if I start to go crazy. All right, so let's just set up a little bit of motivation here. Let's say we have a free smooth G action on a manifold M. Here, M is finite dimensional, G is finite dimensional, everything is finite dimensional. We have a free action. So we have this equivalence of categories. The thing on the left side is G equivariant vector bundles over M. And the thing on the right-hand side is vector bundles over M mod G. For a free smooth G action, these are the same. And the key bit here is that if the action is free, then M mod G is also a smooth manifold, right? If the G action is not free, if we have fixed points, then taking this quotient pushes us out of the category of smooth manifolds, which is not cool. And in particular, for the space of metrics, we have the action of the diffeomorphism group, and that can be absolutely littered with stabilizers, in other words, isometries, right? In the sort of more Riemannian language.
Sorry, just a minor comment. You're not. All you're assuming is that this action is free, right? You're not assuming properness as well.
No, I'm not assuming properness.
You're more than okay with not getting a manifold in the end.
Right. Well, yeah, okay, that's true. Sorry, I feel like I cut you off.
No, not at all.
Okay.
Not at all.
Okay. Yeah. Yeah, I mean, in this case, I suppose that is true. Maybe I should just tack that on to make things even more transparent in future talks. But I still would like to consider, you know, a sort of moduli space where these automorphism groups are remembered, right? And that's what I'll state next here, right? The idea being that a quotient stack is some object, some enhanced version of a space. So I put it in brackets M mod G. Defined so that for any smooth G action on a manifold M, this equivalence holds true. So G equivariant vector bundles on a manifold M are exactly vector bundles on the quotient stack M mod G. And these are really living in the same category because you can make any manifold M into a stack. There's a full and faithful embedding of ordinary smooth manifolds into the category of stacks. So the point I'm trying to make here is that instead of defining stacks and going through all of that machinery, which I've tried in the past in our talks and has not gone well, I just want to answer the question, what does a stack do, right? So this is exactly what a stack does. This says that if you have any smooth G action on a manifold M, we have this equivalence. So we've moved into a new category, but we won't worry about this too much for now. We're just going to make use of it. Okay. And so I'd like to flesh out a quick example here that I think is particularly illuminating. Is one can consider just the manifold being the point with an action of some Lie group on it. This defines a stack, certainly. It's not a free action, but as we said, we could still do that. And indeed, the preceding equivalence on the last slide tells us this, that a vector bundle on point mod G is exactly a vector bundle over a point, in other words, a vector space, and it has the G equivariance property, which in this case just means you have a G action on that vector space. So we recover the category of representations of the group G. And this is pretty slick. So one can, I'm sure, see how such a fact is just generally useful. But I would say that for physicists, in our context, this gives a common context for ordinary symmetries. In other words, these kind of symmetries here, where you just have a plain old representation acting on a field theory, and symmetries manifesting only through coupling to additional data, right? Like we're saying, okay, there's an action of the isometry group. But if you say, okay, well, what if I can fiddle with the metric? Aha, okay, you can change the metric, but then you actually have to consider the entire diffeomorphism group as sort of the symmetry group in that context. So this is pretty cool. This, I would say here, the data on this slide is when I was learning about stacks, I saw this, and that's what made things click. So if anyone present here is looking to learn about stacks, this is one of the key things to consider. I feel like it'll bring a lot of things home. And so indeed, the action of the diffeomorphism group on the space of metrics defines the quotient stack M modulo D. And when we computed this equivariance property, we implicitly used the fact that the diffeomorphism group was also acting on the fibers, not just on the base, right? And so what general covariance really tells us is that, or we concluded that we had a d-equivariant DG vector bundle, and so it has to descend to a DG vector bundle of stacks. A little bit goes into this to say, okay, what's a DG vector bundle over a stack? But I don't want to spend too much time on that now, because we're going to move on to perturbative computations soon. But sort of the punchline is that we can qualify whether or not something is generally covariant by asking, does it descend to a DG vector bundle of stacks? If it does, then it's a family of generally covariant field theories. All right. So just some cultural remarks to put stuff into context. Understanding the space of Riemannian or semi-Riemannian metrics up to diffeomorphism, so the moduli space, is a central problem that's been studied in the 20th and 21st century. For example, computing homotopy types and other topological invariants. And so what we've seen so far in this presentation is that techniques from physics, like looking at field theories over it with other decorations attached to the bundles that are defining the field theories, provide natural choices for stuff to consider. And these produce invariance, for example, like the K theory of the moduli space. Moreover, and I don't do this in this presentation, but it's something I'm working on, if we quantize families of field theories over the space of metrics, and asking if we can quantize them in a way that they're diffeomorphism equivariant is an important step. And actually, sort of the perhaps disappointing punchline is that you often cannot quantize diffeomorphism equivariantly over the space of metrics, but the Atiyah-Singer index theorem quantifies that failure of diffeomorphism equivariance really, really nicely. And this still needs to be put into precise language within the context of metrics modulo diffeomorphism. So work has been done. We're talking about these anomalies in the context of a lot of field theories, but eventually this is the one that I'll be focusing in on. Right, so, well, before I move on, does anyone have a question?
In the middle term here, this metrics modulo diffeomorphism, this I also want to consider as a stack, or what kind of quotient?
So yeah, that's a good question. What I'm talking about in the first two slides here is that people are really just looking at like the ordinary moduli space, right? But there's a relationship between ordinary manifolds and stacks that can sort of make manifest these invariants. I feel like that would be kind of a longer conversation though, but I'm glad you asked the question. Yeah, so in this case, I'm really just talking about metmod diff without considering any stacky stuff. But one can still consider cohomology theories on the stack of metrics modulo diffeomorphism. And it's by and large, it's equivalent to just equivariant cohomology of met, where the equivariance is with respect to the diffeomorphism group. And of course, one could expect to find topological invariance there as well. Yeah. And so the hope is that by looking at, like quantized families of theories and seeing how they fail to be de-equivariant, we would get these topological invariants. Okay, so just a quick preview of what's to come. I just check the time. All right, we're going till 3:50, correct? I'm certainly gonna like to, save some room for questions, I suppose.
You can go until 3:55.
Okay.
We'll give you.
Okay. Yeah. I usually don't max out the full hour, but well, hopefully I won't. Yeah, go over certainly. All right. So just a quick preview. There is a sort of perturbative manifestation of general covariance, and it boils down to some computations which classically live in the domain of physics. But here I attempt to sort of bring them into the domain of rigorous math. So up to first order and epsilon, we can perturb the metric variable, and we perturb it by a tangent vector at that point. So given G, we might consider G plus epsilon H. It's a little bit of an impressionistic maneuver, but we can do it. We can do it rigorously by just computing functional derivatives of the action functional with respect to the metric variable, right? So if you do this, right, if you do this functional differentiation, indeed, if you have, s of G plus epsilon H minus s of G, you'll get this term on the right-hand side here. So if you do this first order perturbation, you'll notice that this first term here is actually just the ordinary action functional s of G, but we have this like first order back reaction to perturbing the metric. And it's exactly the integral of the tangent vector to the metric G, which is a section of some squared of the cotangent bundle, paired with some T mu nu here. And this is, of course, modulo epsilon squared. And this T mu nu here, it looks like this. That might be, a meaningless piece of data, but I needed to include it for completion. And I'll explain in a moment what it is. And so, yeah, the first term is just the action function. We're going to call the second term, this whole integral here, I sub G of H. And T mu nu here is called the stress energy, or sometimes the energy momentum tensor associated to the theory. And it's telling us about the first order back reaction of the theory if we perturb in the metric variable. And physically, you might see in the literature that it tells us how matter couples to gravity. Indeed, if you look at Einstein's field equations, then if it's taking place not in a vacuum, but if it's taking place coupled to some matter, then the left-hand side of the equation is usually whatever includes the metric variable, and the right-hand side is the stress energy tensor. So that it's sort of the source of the Einstein field equations in that sense. And not sort of, it literally is. And there's a key fact here, is that if you perturb, or rather if the perturbation H is induced by a diffeomorphism, it has a special form, right? So before I click next here, the idea is you have the action of D on met of the diffeomorphism group on the space of metrics. And if you fix a metric, you can perturb in a lot of different directions. But you can say, okay, well, what if I perturb along the direction of the diffeomorphism orbit, right? Well, then that H has a specific form. It looks like this. It's exactly the Lie derivative of your fixed metric G along a vector field V, where that vector field V is the one that generates the diffeomorphism that you're considering. There's one important thing to note here before I move on. Because of just the mystery of infinite dimensionality, there are diffeomorphisms that are infinitesimally close to the identity diffeomorphism that are not actually are not just exponentiations of vector fields. This is kind of a weird phenomenon. It only happens in infinite dimensions, but in this case, we're only going to be considering the diffeomorphisms close to the identity diffeomorphism that are generated by vector fields. And so then the perturbation does indeed look like this. And we get that for a closed manifold X, or instead of saying that your manifold has no boundary, you could consider different kind of fields that you're looking at, but whatever. You get this relation here. that this second term in this back reaction that we computed with the action functional, if you do differentiation by parts, you get that this integral is equal to 0, or rather it needs to be equal to 0 whenever the matter equations are satisfied. The matter field equations are satisfied, which here is the Laplace of phi is 0. But then for this to be equal to 0, we need to have this conservation law, that the covariant derivative of the energy momentum tensor is 0. So in that sense, T mu nu here is the conserved current that we can associate to general covariance, sort of in the style of Noether's theorem. Now, I've had sort of discussions with physicists on what kind of conserved current we actually expect in Noether's theorem. And there are a few versions of the stress energy tensor in a curved background that get posited. And it's usually the different kind that gets invoked in the context of Noether's theorem. But I would say that in this case, it works as well. Although I come at it from a different direction. Any questions so far? I know these are kind of technical computations, but hopefully the soul of the matter is somewhat clear. Okay. So there's a very important piece of data that we can associate to a quotient stack at a fixed point in that stack. And it's exactly the analogous version of a tangent space, but for such a quotient stack. And it's called the tangent complex. So we denote it like this. It's bold T sub P at M mod G in degree 0. We have the Lie algebra of the Lie group G, and then in degree 1, we just have the ordinary tangent space. And the differential here is exactly the derivative of the orbit map, right? So T sub P is the orbit map beginning at P, right? So you start at P and then you follow some G orbit in M, and that you're taking the differential here. And so this is a cohomological enhancement of the ordinary tangent space. Indeed, a common maxim that I heard when learning about stacks is that a sort of a tangent complex is to a stack how an ordinary manifold is to or an ordinary tangent space is to a manifold. And really what that's saying even more deeply is that we're moving, just like we move from vector spaces to homological algebra when we want to do the derived version of linear algebra. In this case, we're moving from ordinary manifolds to stacks. So it's like a derived enhancement in the derived categorical sense. So there's an associated formal moduli problem. And what it really boils down to is you're looking at the formal neighborhood of the point P inside the quotient stack. And that's equivalent to this DG Lie algebra, differential graded Lie algebra rather, where you take the tangent complex and you shift it up by a degree. So that the Lie algebra then is in degree 0 and the ordinary tangent space is in degree 1. The reason we do this maneuver is so that the bracket on the Lie algebra is non-trivial within the structure of the DG Lie algebra. In particular, when you take a bracket of two things in degree 0, you get another thing in degree 0, which is what happens if G is in degree 0. If G remained in degree -1, I know I'm not a big fan of this notation, but it's what's commonly employed. If G remained in degree -1, then if we took two things in degree -1 and took their bracket, they would need to land in degree -2, which is an issue because this cochain complex is fully concentrated in degrees -1 and 0. So what we do here is we shift it up so that the bracket is fully manifest. And so this DG Lie algebra sort of inherits the bracket from the ordinary Lie algebra G. And this equivalence is kind of hard to describe, so I don't really want to get into it too much. It's found, for example, in Lauria's notes, the derived algebraic geometry 10. And I think he does a great job describing the equivalence there. But I'll try to explain, at least at the computational level, why this DG Lie algebra here sort of contains the content of the formal moduli problem defined by considering the formal neighborhood of some point P in the quotient stack M mod G. Okay, some water here. So one can compute the Chevalier-Eilenberg cochains of a differential graded Lie algebra. And indeed, they're defined to be just symmetric powers of the dual of the DGLA shifted up by 1. And so if you look at our DG Lie algebra with G in degree 0 and the tangent space in degree 1, and you just work out the linear algebra or the homological algebra, you'll get that it's isomorphic to this purely as a commutative ring. And this is then isomorphic as a DG commutative algebra, or sorry, I meant to say commutative algebra earlier, but a big difference. This is isomorphic to Chevalier-Eilenberg cochains of the ordinary Lie algebra G with its action on the symmetric powers of the cotangent space. And it's interesting to note here that although the isomorphism between symmetric powers of the cotangent space and the Taylor series ring is non-canonical, it's still true. It is canonical whenever the manifold M is parallelizable, then it's fine. But we invoke it anyway. It's not that big of a deal. I think it's just worth noting that it's non-canonical. And of course, this is a lot of sort of like littered computations all over the place, but we're going to do an example in a moment that hopefully makes things somewhat concrete. I just wanted to get people a feel for the underlying machinery here. Okay, so, well, actually, I should ask, I think, does anyone have any questions before we move on? So for those of you that are unfamiliar with Chevalier-Eilenberg cochains, I think the equivalence down here is the key place to take stock of what's going on. So you might have a Lie algebra that acts on a module of it, that it might have, and then you could define the Chevalier-Eilenberg cochains, which sort of contain the representation theory of G acting on whatever module in a derived way. And so a nice concrete piece of data here is that if you consider the Chevalier-Eilenberg cochains of SO2, infinitesimal rotations, acting on a Taylor series around the origin in R2, and if you computed zeroth cohomology, you get exactly the set of rotation invariant Taylor series around the origin in R2. So this is pretty nice. This says that after invoking cohomology, this gives you data that you like, right? Like certainly considering like rotation invariant Taylor series around some point is something interesting to consider. It's interesting in computing integrals. When we learned about Gaussian integrals in our youths, it was certainly an important maneuver. And this is telling us that really these Chevalier-Eilenberg cochains give us a derived enhancement. This is really one of the punchlines here, right? Derived enhancement, a derived ring of functions on that formal neighborhood. So that at cohomology, it gives us what we're used to, but it really contains even more than that. I see someone has something in the chat. Aha, Giannis, thanks. Yeah, excellent notes. Everyone present here should go and read Loria's DAG 10. Or at least the first 2 chapters. Thanks for that. Okay, and so equivalently, ELSA P, this differential graded Lie algebra, describes that formal neighborhood, the formal neighborhood of P in the stack. Okay, so yeah, so you can consider G equivariant functions on a manifold M, and these are really like a derived localization of them. Localization meaning, okay, I'm looking at a point in a formal neighborhood of a point, but I still want to retain the equivariance property, right? In that case, because you're doing these perturbative computations, you no longer have the Lie group G, you just have its Lie algebra, but you still get nice data. Okay. So back to general covariance. the formal neighborhood of a metric G inside the moduli stack of metrics modulo diffeomorphism, excuse me, is therefore exactly this. The Lie algebra of diffeomorphisms at the identity is exactly vector fields. In degree 1, we have the tangent space to the space of metrics. The space of metrics is just a convex open cone sitting inside of sim squared of the cotangent bundle, which is, it's just a vector space. So that's in degree 1. And then the differential here, oh, whoops, that was weird. The differential here is exactly the derivative of the orbit map, which in this case is the Lie derivative of G along whatever vector field you want to consider. And then H0 of the DG Lie algebra, not H0 of the Chevalier-Eilenberg cochains that you get from it, but just from the Lie algebra, are the killing fields. In other words, the vector fields V that kill G when you take their derivative. Of course, that's not why it gets the name. It's actually named after a person called Killing, but I just think it's one of the greatest jokes possible. It's not as good as Schwarzschild being the guy discovering the Schwarzschild solution, because his name in German means black shield, and that's basically the name for black hole. That's probably better, but this is in the top 5 for sure. Anyway, so these killing fields are the infinitesimal isometries, right? So it sort of homologically encodes that data. And so for these, that integral earlier where we paired H with the stress energy tensor is 0 in a really straightforward way, because H is L sub V of G. And here L sub V of G is just 0. You don't have to do any maneuvers, and invoking that you have the equations of motions are satisfied to get that the thing is 0. We're assuming X is close here so that functional analytic issues don't obstruct definitions, but I don't think we need to be so stringent. I'm just forgetting the details as to how we can loosen things up. So just for the sake of getting through this, we'll consider X as closed. And it takes similar care to define the Chevalier-Eilenberg cochains, right? Because of course, these are infinite dimensional vector spaces. This is an infinite dimensional cochain complex. But if you assume that the diffeomorphism group is a Frechet manifold, which you can get by making assumptions on the underlying manifold X, which then also causes the space of metrics to be a Frechet manifold, we can define this quite nicely. We get the Chevalier-Eilenberg cochains of L sub G are exactly the functions on the formal neighborhood G in the stack. And so we could just carry over any finite dimensional notions that we've accumulated by considering the finite dimensional examples prior to this. So next, what we'd like to do is say, all right, we've been thinking about metrics modulo diffeomorphism for a while, but much earlier in the talk, we said, but we have these fibers, right? We have this vector bundle over it, and that vector bundle contains the data of this family of free BV theories, right? So what happens if we take this family, this DG vector bundle, and we pull it back over the formal neighborhood, right? Certainly, those functions on the total space of this pullback, right? So this long tube, as I like to imagine it, should be a module over Chevalier-Eilenberg cochains of L sub G. The comparison here is that if you have functions on the total space of some vector bundle, those functions are certainly going to be a module over just smooth functions on the underlying manifold M, right? So that's exactly what's going on here, except that in the above, it's just this kind of like derived formal enhancement of this picture here. And I would say it provides a lot of geometric intuition. So there's a key bit of data to define here. We have this free BV theory from earlier, and we want to look at functions on this, right? Like it usually would just, if we had a vector space or a finite dimensional vector space, rather, we would just take symmetric powers or the dual of its symmetric powers to get polynomial functions on it. It doesn't quite work out the same way in infinite dimensions, but we still have this maneuver here, which you could view essentially as symmetric powers of its dual. But here now we have the completed projective tensor product. There's a decent amount of functional analytic weightlifting that happens here. It's all described in Kevin Costello's book for those that are interested. But you can really just think of this as symmetric powers, or functions on FG. And so this differential here from the free BV theory extends to functions on it as a derivation. And moreover, for this free case, this induced derivation on the symmetric powers is just Poisson bracketing with the action functional. This here might be familiar to those that know some like Hamiltonian mechanics or Hamiltonian field theory. This is an infinite dimensional version of that. And actually, it's worth noting that one of the sort of punchlines of like the Castello-Guilliam formalism for BV, and really I would say BV in general, is that shifted Hamiltonian dynamics are just Lagrangian dynamics. I know that sounds kind of obscure, but once you learn enough of this and you hear that, you're like, oh, of course it is. And that's kind of a trick. Anyway, so the idea here is that we say that the global classical observables of some field theory are exactly just functions on f sub g with this differential coming from bracketing with the action functional, which you could view as just, extending QG to all the symmetric powers. And the adjective global is here because we're evaluating the cosheaf of observables exactly on the entire manifold X. The classical observables actually define a factorization algebra, which is really nice. And that's one of the big punchlines of my advisor's work. But here we're just going to view it this way. Right. So this here, this O of FG, really the observables are just, they're the functions on a fixed fiber, right? And they have this nice differential. So the preceding computations suggests that the differentials bracketing with S sub G and bracketing with S sub G plus this first order perturbation, which is the bracketing with the energy momentum, the integral of the energy momentum tensor, might define equivalent dynamics, right? So that roughly we'd get something like this. This is definitely a rough statement, but the idea is that if you have the observables on a fixed fiber and then you perturb them slightly along the direction of the Diphyomorphism orbit, those should be equivalent. And indeed, I've worked out explicit maps for these equivalences. It's really quite nice. But it sort of amounts to a perturbative manifestation of general covariance. And at first order in epsilon, this equivalence is, or this equivalence up here is equivalent to the conservation of the stress energy tensor, the covariant conservation that I listed earlier. And so I've been able to work this out to all orders in epsilon, which suggests that we should have like higher energy momentum tensors, right? It's sort of a derived version of the stress energy tensor. I'm still working out like particular computations, but I've gotten some cool stuff if anyone's interested. So moving on, we can now pull back a generally covariant family of theories over the formal neighborhood of some metric G, which is encoded by this differential graded Lie algebra that we mentioned. And we're going to denote this pullback as just the total space of F mod D sitting over the formal neighborhood. It's not great notation, but I needed something. And so we get this theorem is that if you compute the functions on this pullback, you get exactly the Chevalier-Eilenberg cochains of the DG Lie algebra encoding the formal neighborhood with values in the observables. So we have a map. We have an action map of this DGLA on the observables. So we can define the Chevalier-Eilenberg cochains, and it has this really nice geometric manifestation in terms of just looking at the geometry of the bundle. It's worth noting that this implicitly encodes the action of the vector fields, which are in degree 0, and deformations of the metric, which are in degree 1. Sort of puts them on equal footing. And I would say one of the punchlines of this perspective is that just plain old deformations and infinitesimal symmetries are placed on equal footing. We sort of simultaneously consider them in these sort of like L infinity actions. And so in this really nice geometric way, we recover the equivariant classical observables for a generally covariant free BV theory. And that it's not too much of a stretch to do it for an interacting BV theory as well. You just need to do a little bit more bookkeeping in terms of the higher brackets on an L infinity algebra. This is pretty cool. Although I suppose I shouldn't say that because I'm technically tooting my own horn, but I do like it. So just to recap here, one could compute whether or not a family of free theories is d-equivariant, and that's asking, is this generally covariant? General covariance gives that qualification, so we get a descent to a vector bundle of stacks, and computations in a formal neighborhood of some metric in that quotient stack package, but also enhance current conservation results. And basically it just boils down to taking the functor of points perspective very, very, very seriously. And this gives exactly the ring of functions that we desire. That ring of functions, of course, being this thing on the right side here, the equivariant observables. Okay, and so in terms of future directions, what I'll be working on next is by looking at the observables, right? So I didn't write it down that way, but O of F is some observables, bracketing with S is the differential, and perturbing the differential with a new term, H bar delta. This delta here is not the usual Laplacian. This is called the BvLaplacian. And this is essentially how quantization is done, a perturbative quantization, by looking at the new differential, bracketing with S plus H bar delta. From this perspective, one could generically see how a quantized theory shouldn't necessarily exhibit general covariance, because we've homologically talked about general covariance, right? So if you perturb some of the homological data in a way that's not a priori generally covariant, right? You're just adding this new term. There's no reason why the quantized theory should exhibit general covariance. But there's a nice way to quantify this failure. It's called the anomaly, and it's often related to topological invariance via the Atiyah-Singer families index theorem. And hopefully by now, it's clear to you why we need to be considering the families index theorem, right? Because we're really considering families of differential operators. And that's what general covariance is all about. And so that's what I'll be doing with my life next. And of course, I'd be happy to discuss it, you know, if anyone has some suggestions or questions about that. Otherwise, that's all I have to say. And thanks very much.